All right, thank you, Florin. Hi, everyone. My name is Jorge Nicho, and today I'll be talking about ROS, which is a framework for robotics software development. All right, so here's the outline for the presentation. I'll go over some basic introductions to what ROS is, my background, and then I'll be explaining what is ROS. I'll be giving you some history on ROS. Then I'll be going through capabilities, some of the architectural details of ROS, and some basic example of how to program ROS using Python. And then I'll be showing you some resources if you're interested in further investigating, and then I'll open the floor up for questions. All right, so my background is, well, my education, I got my master's in mechanical engineering from University of Texas at San Antonio. I did my master's in robotic grasping research. So you can see some pictures there. Basically, the thesis was about coming up with a method for resolving the grasp between a hand, robotic hand with a bunch of fingers and joints, and any arbitrary object. And so that was a pretty successful research, and I ended up coming up with some very interesting method for being able to find the grasp for as many objects and hands that you could throw at the problem. So as far as career highlights, after I graduated, I worked for Southwest Research Institute in San Antonio. It's a pretty large organization. I believe they had nearly 3,000 employees as of last time I checked, which was last year. And there I worked in the manufacturing robotics department, working on a multitude of robotics related projects, typically in the manufacturing sector, and most of them involve ROS in some way or another. After that, I worked for, and still working for, Blue River Technologies, which is up in the Bay Area, and I've been working there on robotics applications in the field of large-scale agricultural machines. So
Go Road Runners.
Right, there you go. Good to know there's a fellow UTSA person there.
Yep.
I am also a Roadrunner.
Nice, awesome. First time, I think, in one of these presentations. Either that or everybody else was pretty quiet. So anyway, some of the notable ROS projects that I've worked in the past, the one that I can talk about at least. So the more prominent one was the large robot depained project. So basically, this was at the time, and probably still is, the largest mobile robot in the world. And it consisted of a mobile base with, I believe it was 20 mecanum wheels, which allowed for the base to be omnidirectional, meaning it can move and rotate in any direction on a two-dimensional plane. And it had a massive arm, as you can see there, which is the top left picture. And at the end of the arm, there was a tool that had a laser that was used for paint stripping. So this allowed for the robot to go around the plane body and remove, coats of paint so that it could be inspected for imperfections and problems. And so anyway, this robot was actually unveiled a couple of years ago, I believe. And it's, as far as I know, is operational. But I actually participated in the development of the parts of the navigation system for this project. The other project to the right of that is the robotic sanding project. It also used ROS, and we basically were doing what is called robotic blending, or sanding in this case, meaning we go over the part and we sort of use a sanding tool and remove imperfections from the part, which are usually common to find those in parts that are just manufactured. These are, inevitable, and so you have to go with a sanding tool to remove those. But in this case, we used a robot as opposed to a human, and so we were using all kinds of technologies, motion planning, perception, collision avoidance, and that sort of thing. And then the one other project that was also pretty interesting was the the bottom left, there's that box with some markers coming out. We were using that to, a camera that was on a robot was tracking that tool, which we moved around, and we were teaching waypoints to the robot, so then the robot could then execute a task as it was taught. So this was basically a robot teaching project, and that was actually pretty successful. We were able to very, use that system to teach the robot a bunch of tasks using this particular perception system. And that autonomous navigation, that was a pretty old one. I actually don't remember a whole lot of it, but it basically entailed having that robot on another mobile base to draw. It was an experimental, like a research project, to draw patterns on a surface while the base was moving. So it had to coordinate robot arm motion as well as a base motion. So technical expertise, a result of working on a bunch of these types of projects, I ended up learning a lot about ROS, ROS2, of course, C++, which is probably 80% of the time what was used for a lot of these ROS projects. Occasionally Python, and then of course you have to use IDEs, a bunch of simulation environments. A lot of it was done on Gazebo when I needed to, Gazebo being the simulation environment for ROS. Although you can use some other ones, but that's the one that it's more compatible with ROS. Of course, you develop your ROS applications in Linux. I usually use the Ubuntu distribution, but you could use a bunch of others. As far as I've been told, I haven't really tried using anything outside of Ubuntu myself, but likely you could also do ROS development in other Linux distributions. And I also use a bunch of robots from industrials like KUKA, ABB, to others that are not necessarily industrial ready, like Universal, but are still pretty robust platforms. So those are some of the tools and various things that I've learned from being involved in all of these ROS projects. So what is ROS? If the opening slide said it's a framework, even though ROS itself stands for Robotic Operating System, but it's not really an operating system. It just sounds cool, but in reality, it is a framework for developing robotics applications. It provides a bunch of capabilities and tooling which are commonly used for robotics applications. And the main thing that it does is that it avoids reinventing the wheel on things that have already been done a bunch of times. So every robotic application likely will have a need for collision avoidance or collision checking, for some type of perception, for some message passing. There's all kinds of things that you always will have to do in robotics applications. And so ROS kind of gives you a lot of those out of the gate. And so you don't have to spend time reinventing the wheel, so to speak. And you can focus on, novel capabilities or features. And so that's what helps advance the field forward more efficiently. There's lots of industrial support for ROS in the form of drivers for various peripherals, such as cameras, joysticks, all kinds of sensors, and also robots, which is a very important piece of this. There's standardization, which is basically common interfaces. So that way your applications can be more portable, or you can even swap around applications that do slightly different things, but still require or act on the same input. And so you don't have to change or rewrite a whole chunk of your code when all you really need to do is to make a minor tweak, because the interfaces are the same. And so you only have to change what's relevant to the feature that you're changing. The license that it uses is Apache 2.0, so that's pretty permissive as far as I know. Don't ask me much about IP considerations because I'm not an expert, but I just know that Apache is a pretty open, and so you won't run into too many issues with IP concerns. And there's a massive community for ROS. You can go to ROS Answers. That is a website. Of course, GitHub. There's the main ROS repository, but there's a bunch of adjacent GitHub repositories for several other capabilities that are used with ROS. And there's also a page in Discord as well, so you can go there and ask questions or maybe even find tutorials and things of that sort. So this is sort of a very simplified depiction of what ROS is. So one of the things that ROS is plumbing. So meaning, you have a bunch of, ROS is built as a set of separate applications that are talking to each other, right? There's an application for perception, maybe one for motion planning, another one for collision checking, and perhaps some other custom one that is only relevant to, your robotics application, but all of those need to talk to one another. And so in order to do that, ROS provides mechanisms for sending messages and receiving messages, or calling services and responding to services. So that's what in this slide, I've called plumbing, right? The way in which data is being passed around through the various applications in your ROS system. And in addition to that, there's tooling. So there's already built-in tools for doing, things that you would always do. One of those is the visualization tooling. So ROS has RViz, which is basically this software that visualizes a lot of your data that comes through, right? So you can visualize images, you can visualize point clouds, you can visualize, like if you have a path that the robot's following, you can see that in RViz, and you can add additional things that are even interactive. They call that markers. So there's that tool, but there's a bunch of other tools for doing system introspection. So you can bring up, it's called RQT window or console, and you can see like what a node is writing to the console. And there's all kinds of tools that are, provided to you when you install ROS, which you don't have to develop yourself. And that makes it super nice to be able to develop with it. There's capabilities. So capabilities refer to kind of more higher level things. So for instance, if you want to do, observe or detect an object, there's a, perception capability that handles that, right? Or if you want to do motion planning, you have an arm and you want the robot and effector to go to a specific place. There's a whole process which involves generating a motion plan so that there's a, the robot knows how to go from where it is to that goal point or goal position. And so that motion planning is a capability in ROS. And there's a bunch of things of that sort that are higher level, but allow you to actually do meaningful things with your robot. And there's the ecosystem, which is kind of everything together, in addition to the people who are involved in how you access those resources, such as like I mentioned before, Discord or GitHub, and all of those resources. History of ROS. So the project began in Stanford. So two individuals who recognized the problem with how little progress was being made in the robotics field, where a lot of these different projects spent so much time rewriting the same things, and they decided, well, let's go ahead and fix this. This is really keeping us from further advancing the field more quickly. And as a result, they decided to build ROS. That was the main motivation. They just wanted to provide a framework that had the things that you would do anyway, so that you wouldn't have to do them. You could focus on the novel stuff. And that's basically how ROS ended up becoming what it is. It was in that sense, it definitely was very successful. But anyway, as far as like the time frame when all of this happened, so after that initial stage where it went from an idea to an actual tangible thing, it was led by Willow Garage back in 2008. So they started to release the first versions of ROS back in the day when ROS was still ROS 1, right? The first version of ROS. So the first distribution was released in 2009, which I actually never even used. And then OSRF eventually took over ROS because I believe Low Garage was disbanded. And in 2013, OSRF took over, and they've been maintaining it ever since. And around 2015, the development of ROS2 started, recognizing that ROS, as good as an idea and as good as it might have been and useful, had too many limitations. And so ROS2 was the answer to all of those issues. And eventually they identify all the different problems that the original ROS had, like a single point of failure. There was no real-time support. There was no sense of security of any sort. Network connectivity was not flexible. And, if you had multiple robots in your system, that was never easy to do. It was doable, but you couldn't really do it very seamlessly. So anyway, in 2015, ROS2, the alpha version at least, was released, and that's basically the version that people have been using up until this point. And so you can see on the right-hand side, all of the various distributions. This is a little outdated now. There's actually I think a couple more releases that have come out since that Irwin release. So you can go into ROS.org, I believe, and see what those are at the moment. So applications that are built with ROS. So you can name the field. It probably has a ROS application that somebody has tried to write. But ROS has been used in agriculture for fruit picking or plant picking, and then there's warehousing. You're probably all familiar with robots in warehouses and Amazon sites and whatnot. So a lot of those were built with ROS. Bin picking, that's a very common one. It's one where I've seen a lot of companies, or some companies, use ROS as their initial, or at least their main solution for that. ROS has been used also a lot in industrial manufacturing, from robotic painting to fastening. So like on the bottom left, you can see those robots, and maybe it's not all that easy to see, but they're actually putting fasteners on that. I think it's a plane fuselage there. So that's what those robots are doing. And there's, of course, ROS being used in academic research and all kinds of very novel things. So ROS capabilities, I've sort of touched on this a little bit before, but basically, it's all of the high-level pieces that make your application come to life, right? So motion planning is one of those, is one that I'm pretty familiar with. But then you also have computer vision, which is obviously, in most cases, very application specific, depending on what you want to sense or see. There's hardware drivers, which is a very key one that doesn't get a lot of exposure, or at least it's not the more flashy one, but definitely is very powerful because it enables all the different pieces of hardware in your system to talk to one another, right? So you have a camera, you like to at least purchase one that has a ROS drive for it. That way you can get the images. Or if you have a LiDAR sensor, for example, you definitely want to look into the one that provides a ROS driver. That way you can get the point clouds as easily as possible. But there's also robots, and a lot of industrial robots actually have provided drivers with varying degrees of support. So it's always, it makes it at least very easy at first to start having some initial functionality when you have a ROS compatible robot. And just like that, there's a bunch of capabilities that are already provided. I believe there's also a navigation capability for having a robot basically find its way through a building or some type of landscape. There's a library that has been around for quite some time that it's already easily usable within ROS. So these are just basically a list of robots and sensors that I know are compatible with ROS, but there's probably a lot more. This is a tiny list, but you can see there's at the very top there on the left. Those are industrial robots, and those provide ROS drivers that you can use in your robotics ROS application. there's all kinds of research type robots like that Boil of the Rock PR2, which I believe you can't get anymore. That was like one of the first ones, but there's all kinds of research type robotic platforms that do provide ROS drivers so that you can start investigating.
I have a QBO.
You have a QBO, nice.
Lower left-hand corner.
Yeah, I see it. Nice. How do you like it?
Huh?
How do you like it?
Well, it was okay when it worked. It came out in 2012.
Oh, okay. Wow, that's a while ago.
Yeah.
Nice. All right. Okay, so since AI is sort of the rage nowadays, I kind of have to include a slide or two about what AI and ROS are, integrations are around, and it really is application specific. ROS itself is more of a set of tools to write robotics applications, right? And if you have something AI related, like a learning module or something along those lines, you usually write it ROS independent, and then you wrap it around ROS code. But anyway, there's already existing things you can use out of the box. I haven't used these personally, but I was doing some research to see what was out there, and a lot of it, just like I've seen in the past, a lot of it is along the lines of perception, right? So this is what you're seeing here is a object detection capability provided by NVIDIA called ISAC ROS object detection. And so basically it uses a trained network or model to be able to detect objects in the environment, right? So on the left is the object detection, but then there's also a pose estimation, which is a similar principle, but rather than detecting the object, it just figures out what the object's pose in three-dimensional space is, and it gives you like the bounding boxes, which is very useful for like some initial perception tasks, especially in like a bin picking application. I could see this being a very useful thing to start out with.
Jorge, quick question.
Yep.
Does the new commercial robots like the Tesla robot or other robots, do they use the ROS system or they have their proprietary system?
So it depends on the vendor. I would say in a lot of cases, I've seen that new robotic platforms that come out, at least research style robotic platforms, they do provide ROS drivers for it. As far as industrial robots, that's a hit or miss, right? I think a lot of industrial robot manufacturers are, to some degree, on board with supporting ROS, but the degree of support that you get varies from vendor to vendor. So you kind of have to do, like, depending on what you're doing, you kind of have to do your own research on the degree of support that you'll get with if you use ROS, right? But I would say even if there's no ROS support, a lot of it you can do in ROS, like all of the reasoning, all of the logic, all of that. It's still far easier to do in ROS. And then at the end, you would just write a translation layer that takes whatever output ROS gives you, and then translate it into what the robot wants.
Okay, thank you.
As opposed to the alternative being, which is something that I remember was still a problem, and maybe that's still in some companies still being done this way, but you would write everything that you needed to do, including the perception, the motion planning, in the robot specific language. So every industrial robot arm or industrial robot that you purchase, each vendor gives you a robot language that is specific to them, right? So people write all of their software, all of their applications in that language. And so portability was obviously impossible, because then if you wanted to use a different robot, you have to rewrite everything that was in that vendor specific robotic language to this other, right? And so that's where ROS kind of makes that a lot more flexible, because you don't have to be vendor locked as much.
Okay, thank you, Jorge.
Sure. Some other interesting thing that I found, which is not perception related, but still uses AI, is this tool that it's still at its infancy, is more of a research thing, but basically it's a way to kind of chat with the terminal to ask it ROS things, right? So if you have, when you develop your ROS application, you'll have what they call nodes, which are, applications running that are doing ROS things. And so rather than typing the actual specific command to, locate or show you what those are, you can just do like an AI ChatGPT style query and say, hey, what are my nodes? And it'll figure out what the command is because it's been trained on that, and then, run the command for you. So that's sort of a neat thing. I don't know how useful it would be, but, it's one interesting integration between the current AI and ROS. Okay, so now I'll jump into ROS architecture. So this is a very, hopefully clear depiction of what is going on when you have a ROS system. So usually what you do is you start by writing a node, which is essentially an application with some ROS, some ROS interfaces built into it. And your node is what is doing the work needed, right? So you would have a node, for instance, right? A node that does your perception logic, and another node that does your motion planning, another node that's doing data logging and stuff of that sort, right? So all of those nodes or ROS applications are doing that on their own, but there are points where they have to be able to communicate with one another in order to coordinate what they do. And so those interactions are facilitated by way of topics, services, parameters, and actions. So the more common interaction is that of a topic, right? So in that you have a publisher subscriber model. So let's say I'm a camera driver ROS node and I'm publishing images that I capture with the camera hardware. So I will advertise that through a topic, and then there'll be, for example, a perception node that wants the image to do some processing. So that node will create a subscriber, and it will subscribe to the topic where the image is being published, and so it'll get the image that way. So that's a very typical ROS interaction, the topic and subscriber publisher model. But there are other kinds that are that have a different dynamic, such as the service, where you have a client and a server, and the client needs for the server to perform an action of some sort, right? So for instance, if you have a robot or a ROS application that needs the robot to move to a specific point, then rather than using a topic for that, you would create a client to a server that already exists, and then you would call the server, and the request will be something along the lines of move the robot to point X in the map. And so the server will get the request, process the request, finish the request, and return a result confirming that the action was carried out as asked. And so those are like the two most common interactions that you can use in ROS. There's also actions, which are similar to services, but there's a little bit more nuance to them in that you can monitor the progress of how the service request is being executed. But in essence, it's basically a service client type interaction with a little bit more nuance to it. There's as far as programming languages, there's full support for C++ and Python. Of course, C++ will be more high performance, but sometimes you don't need all that performance. You can use Python, which makes things easier to write. There's, as far as I know, some experimental support for Rust if you're using that. I believe at one point there was some Java support. I don't know how much attention that is getting nowadays. Probably not a whole lot, but those are your options for jumping into ROS programming. So this is a more elaborate schematic of how ROS is architectured. So ROS basically, everything that I described in the previous slide about the publisher, subscriber model, and server and client interactions. So all of that communication happens through DDS, which is data distribution service. So you have DDS at the very bottom layer, And then on top of that, you have what is called the ROS middleware, which are wrappers around DDS implementations, right? So those are basically the piece of code that enable for all of these communications and interactions to happen in ROS. And then, you go one level above that, and you have what is called as the ROS client library, right? So these are the layers where you can use to create services and clients and all of those things to then build your actual ROS application. So this is more or less how ROS is broken down, right? This is something you don't usually touch for the most part. In fact, I rarely ever dealt into any of these, but the one that is at the very top, which is the user application level, right? But for the most part, you won't even have to do much on those other deeper levels if you delve into ROS. But it's always good to know how things are structured. That way, it gives you a better understanding of what's going on with your application when you're debugging. So with that, I'll jump into some programming. These are Python examples, but like I mentioned, you can write just about everything in C++. In fact, that's a preferable way to do it in C++, but Python is a lot easier to write and also explain. And so I'll be using Python as the programming language for these examples. But essentially, let's say we want to be able to advertise a message, right? So what we do is we start creating a node, and we call it talker, and we have our main function, which most of us probably seen if you've ever been a Python program. So you kind of have to call that ROS py init at the very beginning. It's just how all ROS applications are initialized. You got to have that. And after that, what you do is you create a node, right? It's another mandatory ROS requirement where you create a node. A node is like the sort of entry point to everything related to ROS in your code. And after that, you create using the node that you just created, you create a publisher, which you're going to use to then publish your message. And you have to call it something. You have to call the topic something, right? So in this case, we're going to be so creative to call our topic. And then that gives us a publisher. And after that, we create a message, which is this string, a line, and we go into this while loop. And all we're doing here in this while loop is we're populating the data field of the message with a string and some index, right? So every time we go, on the next iteration of the while loop, we'll be incrementing the index. So that way we get a new message, or we publish a new message each time. And after that, this node get logger line is all it's doing is writing to the console. So you'll see if you run this node on the console, you'll see publishing message, and it'll print what message it is. And after that, you publish the message, and that'll basically send the message out into the topic, right? So at that point, once the message is being published, if you were to go into your terminal and you type ROS topic list, you'll see that there is a topic called topic, and you can even echo the topic to get the messages that are being published through it. So this is just the first part of that, right? So you're now publishing a message, but now you want something to be able to receive the message. And so for that, we write a listener. And in a similar way, we will start with a main function. And like I mentioned, you've got to have this init call is just how you initialize ROS. And then you also create a node, right? So the node is, again, one of those mandatory ROS requirements. And once you have a node, you create a subscriber. So in the previous slide, we created a publisher, but we're going to create a subscriber to subscribe to the topic and get the message. This is a mistake here. It should be topic rather than chatter, but let's assume we actually used chatter on the previous slide. I should probably fix that at one point. Anyway, we create a subscriber by telling it who do we want to subscribe to, and so we tell it the chatter topic, right? We also have to tell it what data type we're receiving through that topic. In this case, it is the string data type. And then what we do is we provide a function callback, which we're going to use to receive the messages. So this chatter callback function has one argument, which is the message itself that it's going to be receiving through it. And then in this case, we're just going to take that message and print into the console what the content of that message is, right? So that data field, which is what we populated in the talker program in the previous slide, is what we're going to be using to print into the console. So once we do that, then we enter this while loop, which is only checking that ROS still running. So that .ok is all it's doing is checking, is ROS still running? Yes, and then so it'll basically be caught in the while loop, receiving messages. And you have to spin ROS is just another requirement. When you're receiving messages, there's like a queue of messages that builds up internally. And in order to process those, you have to call this spin method in order to process the queue. And so that way the callbacks get the messages and they get processed. And once you kill the application in the terminal, then you exit the while loop, and then you call these destroy node and shut down to stop ROS. And that's basically the simplest example, is like the hello world of ROS, right? This is how you go about publishing messages and receiving messages. But obviously, there's so much more that you can do with ROS. In fact, one of the other things you could do is write services that I mentioned earlier, right? So in this case, we're going to write a server. So let's say we want to advertise that the fact that we can perform a task. In this case, our task is adding 2 numbers, right? So then in order to advertise that, what we do is we create we have our main function, and then we call this minimal service class, right? So this class, all it's doing is providing a callback to service the request, right? So this add to ends callback is basically going to handle a request that may come from another client in a different ROS node. But essentially what it's going to do is it's going to grab the request, it's going to access the 2 fields, A and B, which are integers, and then it will add them up and put the result back in the response. So the response is what gets sent back to the client, right? So it's a very simple computation, but it shows the principle, right? You can do something very complex if you wanted to, some crazy math formula. And at the end of the day, you put the result back in response. Of course, this, you're not limited to just this request type. You can define what the request is. You're free to define what fields go into it. It can even be a very complex data type, and you just have to provide a way to handle that. But regardless, so you back in the main function, you create your server, and then again you spin it, and then that's basically what you do in order to create a service. And then the client side, you want to call the service that you just created. So in that case, what you do is you build the request, right? So here in the send request function, what you do is you create the request structure, and then you populate it with A and B, which are the 2 fields that will be added by the server. And then you call this call asynchronous. And basically, when you do that, it'll send the request to the to the server, and the server will then handle that. But in the meantime, you can either choose to do something else, or in this case, like we're doing in this example, we can wait until the request completes. And so that's what this piece of code is doing. And so it'll hang in there until the server returns and with a response, and then you can then exit the function. And that's the basic workflow of how a client and a server interact with each other. Anyway, any questions on that?
Yeah, so if you are like to use a AI model, let's say, like for example, this robot, like I'm training it, and then I'm trying to use it. Like, should I create like one of these servers to actually call the model? Is this something like because like you create a server when you have something that's like requires like heavier compute, or what's the kind of the main idea there? Like if I was to use an AI model, let's say for an ARM, why would I create it? Would I wrap it into one of these servers, or should
Yeah.
I create it?
Right. So let's say you have this AI model that you train, right?
Yeah.
You want to be able to use it, but you want to use it from different applications, right? So rather than having to write the same logic that loads the model, queries the model, gets a result in every single application where you need to use it, you could just write the service, and then every application that needs something for the model to do could just call that service and get the result. And so it makes it easier for that particular capability to be used by all kinds of other applications.
Yeah, so you're basically building an inference service.
Yes.
Yeah.
So I have a question. You said there's asynchronous messaging is the way to do asynchronous. Why would you have a asynchronous as part of a service? Is there any difference in these two approaches?
Why would you have it asynchronous? Well, it's so that you have the option to do other things while you're waiting for the response, right?
Yeah, but when you do the topic, it's in essence asynchronous, right? So you're sending a message and somebody's listening and then pushing it back. It's kind of asynchronous messaging, right? So is there a difference when we do async as part of a service?
Well, so in the topic, there's no response, right? So you send the message, but you don't wait for the response to come from anything, because there's not a response involved in that interaction.
Okay. Sounds good. Thank you.
Yep.
I also have a question. What is the minimum computer power that you require? What is the smallest device that can go on the node?
Well, so that's typically application specific, right? So for example, if we take Florin's case, right, where he was talking about an inference model he had trained, then the requirements would be dictated by that. But as far as just writing the ROS layer, which would involve the server and the client, I mean that is so the requirements with that are so minimal to where it wouldn't really matter all that much. It wouldn't put any computational burden that is significant.
Yeah, if you look at, just as an example, the Create 3 educational robot, it runs ROS 2, I believe, and then you can add a Raspberry Pi 4 to do more functionality with ROS.
Right.
Okay, thanks.
Yep.
So I have a question.
Yep.
So let's suppose like you're creating a robot arm like to move in a certain XCY global coordinate position. Like how would we create it to the Python client? Like do we write a client in the client file? Do we mention the global and coordinate positions of it for the robot arm to move?
So there is a ROS library called MoveIt, which does that computation for you. So they provide a ROS service which you can call, where you build your requests, and the request basically you have to define where do you want the n effector to go in your coordinates, right? Whatever coordinate system that you're using, you would say, I need to move the n effector to X, Y, and Z position in this orientation. And so that server will kind of handle, will compute the movement required to get the end effector to that particular point.
I mean, if you give your TF coordinates in the ROS simulation, is it that going to work rather than this? Like just for simulation part?
As long as it is reachable by the robot, it should work.
Okay.
Right. So the robot, it has to do with the robot's ability to be able to reach that position and orientation. And if it's feasible, like within its physical parameters, it should be able to reach that, or at least move it. Should be able to give you a valid pose for that.
Okay. Okay. Thank you.
Yep. All right. Well, with that, I have some resources. I suppose there might be a way to share this slide later. Soren?
Yeah, if you send it to me, I'll post it. Most likely it's going to be on a YouTube video. I'm going to post it.
Great.
Yep.
Yeah. So anyway, these are some resources you can go to. There's of course the official ROS page, and it's got a lot of the information that I just presented, as far as how to write a note and that sort of thing. ROS Answers, which is a portal where you can go and find commonly answered questions. There's a bunch of tutorials and even training material that you can follow with very elaborate examples. In fact, I think for that ROS industrial training, I did participate in creating some of those. Back in the day, I used to be a ROS trainer when I was working for Southwest Research, so I built some of those training modules since we provided training for people from various industries. There's also the ROSCon archive. So there's been a ROSCon or ROS conference. I don't know since when, but basically every year for the last 10 years at the very least. And all of the presentations are you can find those there. And some libraries that I have been mentioning, a few of those, but MoveIt 2 is one of those that I've used a lot. It uses or basically handles motion planning for your robot arm. And then there's a point cloud library, which is not necessarily a ROS library, but is used heavily within ROS. So this is just to do processing on point cloud data, which is something you would be heavily using if you're including LiDAR sensors or cameras that give you some sort of 3D data. And ROS AI, there's, like I mentioned, that NVIDIA capability that I presented in one of the slides. So you can go and take a look there if you're interested in finding out more about that.
Yeah, question about NVIDIA. Do you know of any integration between NVIDIA frameworks and ROS?
Well, so the one that I know is they have a simulator. In addition to the ones that I've presented just now, they have a simulator called ISAC, which has some degree of integration with ROS, meaning you can, I don't know if you ever play with ISAC, but you can bring it up, and then ROS has this sort of world representation through URDF files. And so in the URDF file, you define your robot and objects that are in the environment. So to a degree, I believe ISAC can use those URDF files for ROS and then spawn the same objects in the simulator. And it can also model joints and motors and actuators and those kinds of things. So that way you can have like sophisticated control logic to drive the actuators in the robot that is being simulated within ISAC. So there's some degree of integration between NVIDIA and ROS.
So I just have a question. So let's suppose for the industrial robots, like the Fawn or KUKA robots, which do you think is better? Like they have their own teach pendant language, and they also can be integrated with ROS and different vision systems, and also computer vision applications. So which do you think is better, like for more optimization and efficiency? Is it using the TPP language or integrating it with ROS?
No, I would definitely prefer integrating it with ROS because I don't know if you've ever been exposed to a teach pendant language or robot specific language, but those are very specific to what the robot does, and a lot of times they're not very intuitive, and like things that are very easily done in other languages like C++ and Python, which is how you write ROS, you aren't able to do in the robot programming language. So I would say the robot programming language, if you have to use it, you would use it only for the things that are very specific to communicating with the robot, but not to do involved computations.
Okay. I mean, the teach pendant languages are basically the joint velocity, basically the kinematic and dynamic parameters of a robot, right? So I was just curious, like, do you want it to make it like write it in a program form and then complicate it in ROS, or just directly put in the joint and coordinate positions so that the robot can move in different angles and everything? So, yeah.
Yeah, so that is sort of application specific, but in some cases, in most cases, you would want to just use the functions for commanding the robot to move, right? So at least the way in which we typically wrote robotic applications, where at the end we had to get the robot to act on something.
Mhm.
We would do all of the like inverse kinematics, for instance, right? We already had like the kinematic parameters of the physical robot into our ROS application. So we would use, our kinematics to resolve for a given pose, and then send that onto the robot. Where on the other side there was some small script with written in the robot programming language to first get the data and then call the relevant function to act on that data.
Mhm.
But most of the processing was done on the ROS side, mainly because you can write that in C++ or Python.
And also, do you have any suggestions like to learn ROS with Python associated, like not the ROS official document and tutorials in it? Do you have any other recommendations of any textbooks or any YouTube channels you know of?
Not of textbooks. Well, so I know of this website that provides ROS training called a Construct.
Yeah, I've been with it. Yeah. I mean, it is, yeah, the construct free programs are good, but like if you want to get into a deeper version of it, I think it's it is very pricey. So yeah.
Gotcha. Yeah. Other than that, I would let's see. So I would go into the ROS industrial training material there. We had some still. I mean, they wouldn't be as involved as a full blown, industrial grade robotic application type tutorial, but you get something that could give you a far deeper dive than what I would imagine you would find in the ROS main documentation.
Okay. Thank you.
Yep.
Have you used any of the LLMs like Claude to write ROS code?
You mean like ChatGPT or something like that?
Yeah.
To ask it to
Yes.
write ROS code? Yeah, I mean,
Yes.
I've used that casually, just like not just for ROS, but for like other things, code for other projects that are not ROS specific. But I usually just ask it, use it in a sort of very casual, in like for things that are sort of separate. I ask it, hey, I want to do this. How would you write this sort of thing? And get an answer. And I still put a great deal of time making sure that it looks correct, right? Before I decide to use it, but not in a, what do you call it? What's this new trend that I've been hearing about? Vibe coding. I never used it.
Yeah.
Yeah, never used it in
No.
a vibe coding sort of way.
Well, I guess my question is, does it, have you found it does pretty good rather than having to go out and search for an answer that you don't have? You can ask the LLM and it's actually fairly accurate.
For some rather surface level things, it definitely is. But I haven't really tested the limits of it. Like if I wanted to do something as involved as what I was writing, when I needed to do full blown, industrial grade applications, I never really, at the time it wasn't available either. No, actually it was, but I didn't use it for that sort of thing. So I couldn't tell you exactly how far it goes on that, but I feel on other work that I've done, where there's libraries that are already in place, which are not public, I would say it's probably not going to do very well because it doesn't know about the library,
Sure.
or even if it gets exposure to it, it's so complex, it's just unable to make enough sense of it to give you a proper answer.
Sure, I would expect, mainly getting help from public, libraries and subjects and stuff like that.
Right.
How far can you get with Python, and when do you actually have to drop to using like C++? Like how much? Yeah, like I'm personally prefer Python, but
Of course, yeah. So for things that involve either motion planning or like more than the just the base level case, right? Or perception, especially involving the point cloud library, I would use C++.
yeah,
So, for instance, I was using a LiDAR sensor, right, or a stereo pair camera where you get a point cloud. You needed to do, some involved processing of the point cloud. Then the point cloud library, which is a C++, library, would be what I would use by default. And so I would use C++ in those cases. I believe there might be some libraries already out there for doing processing of 3D points. But it's the one that I was comfortable with, the point cloud library, that is. And so I use that. And like I said, the same for motion planning type systems.
got it. Well, thank you.
Yep. All right. Well, thanks so much.
Well, thanks so much. Yeah, awesome talk.
All right, great. Appreciate you guys inviting me.